everybody. This is Paul Taubman with 9.Connects. Thank you very much for joining us here today. We're going to be talking about basically cable and wire, connectors, and everything else, oh my. And there's quite a bit to cover today, and obviously we won't be able to cover everything that's out there, but I certainly got a number of slides for you, and as usual, I've created more slides than the amount of time I have available, so we're just going to jump into it here immediately. So what we're going to do, first and foremost, just to give you a little bit of an overview of our objectives for today, we are going to talk about cabling and wiring, go into a little more detail about that. We're also going to talk about connectors for a few minutes, and then we're also going to talk about drawing in general. I won't have time today to answer questions, unfortunately, just because of the amount of time. I'm going to probably take it just slightly over the hour. So please do type in questions, and my colleague Jeff Condit's also going to be on the line over here viewing those questions. They'll be able to try to answer those questions in real time. So feel free to type those in at any time you want there. All right, so with that being said, let's jump on over here to our next slide. So as I mentioned, there's just so much information that obviously can't cover this all in an hour, so let me give you some pointers and references to go to. The specification that may be of the most interest to you is the IPC-A-620 requirements and acceptance for cable and wire harness assemblies. It does come from the IPC, and it's obviously something you got to purchase. Just to give you a heads up, though, it is currently under committee, so there may be a new one coming out here in the next year or two. So I just want to give you a forewarning that if you purchase it now, there could be some changes coming up here soon. Secondly, there is a training manual and that has come out from IPC. I don't know how old it is, but it's really a wonderful manual. I did purchase it, and it's called the IPC-DRM-WHA. And you can see a copy of this over here, and we'll provide you the PDF link if you want to see what this looks like. It's a really neat little manual. It was specifically written for those people on the test floors or on the assembly floors who may not necessarily have a college education, but are doing this stuff time and time again. And it shows everybody, whether you're an engineer or a technician, how to basically properly crimp certain things depending on the class that you're trying to build to. So the pictures are wonderful in it. The information is presented in a way that anybody can really understand it. So take a look at it. If it's something that you're interested in, you can certainly purchase that from the IPC. I was very impressed with it, so that's why I wanted to make that available to you. There are other specifications out there that you may have to obtain if you're going to do any type of cabling. So if you're going to do, for example, fiber optic, Ethernet, USB, those type of things, there are certainly protocols out there. Some of them you'll find on the internet free of charge. Others you have to pay for. That's just unfortunately a fact of life here in our particular industry. There's also specifications that are particular to an industry or company. So for example, Cisco certainly has their specifications on cabling if you're going to use their products for your internet needs. So just keep those in mind as well. There are also a lot of cable companies out there, connector companies, that have these manuals because they know that a lot of people have not necessarily been trained in this, so they want to try to provide their information to you, not just their product lines, but just what the industry it provides and what the terminologies and jargon that they make use of. And so you can take a look. One particular book that I leaned on quite a bit here for my presentation was a company called Annixter. I worked with their technical folks. They were very kind enough to fill in some of the blanks that I couldn't fill in while I was working on this presentation that you'll see here today. But they came up with a really phenomenal technical handbook. And again, it's not just their product, it's all the product out there. So it's well over 300 pages of really some good stuff. And again, we'll make this link available to you in the chat if you're interested in it. All right, let's get on to it. Oh, a couple other things or thoughts here too. Obviously, your colleagues who have been there and done that, you want to talk to them about cabling. So those who've learned from their experiences, you yourself may have learned through a couple of experiences. If you're going to work with cabling reps and connector reps, obviously ask for samples and demand that they demo it. Unfortunately, it's what we found in the connector industry quite often is that they'll put out a product line and it's been obsoleted almost as fast as they introduce it. So just be aware of that. And then lastly, your company technicians, to me, I think they're a wonderful resource. If you're in a company that does have these technicians, talk to them because they can tell you which cables they've worked on in the past, which tooling they already have in-house for these particular cables, the most reliable cables that they can put together, the ones that are a hassle for them or the least reliable. They'll be more than happy to provide that wonderful knowledge to you if you ask them. And then, of course, lastly, here at 9.Connects, if you need any help, we certainly can do things above and beyond what's done in the board. or on the board level here. So if you're trying to do a system level design, we can certainly do that for you. We have experience in cable types and connectors. If you need artwork done, we would do it in Zook and E3. Excuse me. And then for E3, we are the value-added reseller for this particular product. So Zuken does do printed circuit boards, but they also have a cabling and system tool out there. We do represent just simply the cable and the system tool. It's called the E3. And I will be making references to this today, but I will not have time to demonstrate it. If you're interested in what we have to say about it, you can certainly contact us and we can demo it at another point in time. With that, let's jump on into this. Most of the people who are probably in our audience today come from the PCB point of view. And if you're coming from the PCB point of view, we have to do a little bit of a twist of our mindset in a couple of areas. So first and foremost, for components, a lot of times we purchase a component for our printed circuit board. We need a resistor, we declare a resistor, and we're done. And it's just a single line item on our bill of materials. However, with cables, we may have to purchase several things for it. So for example, if we want a very specific cable, we might have to purchase the housing, we have to purchase the pins, the back shelf. So there may be several line items that we have to take into consideration here. Secondly, for the cabling, when we're going from point A to point B, we don't really worry about the trace. That's really the fabricators need to worry about. They figure out the copper. We have to tell them the copper weights and those kind of things. But really when it comes down to it, we simply with the printed circuit board, we say we're going to connect from point A to point B, and we give a trace width. But with cables, there are just hundreds of different types of gauges and strands and insulators, and so we have to be we have to call those things out, and that takes a lot of time to figure out, especially for the application you're going to use it in. Excuse me. And then for component attachments, we use solder mask, or we use the solder, or we use the solder paste, as opposed to a cable where it's really a combination of basically solder and of a pressure fit. A lot of times we have to use a tool for that. And then for the point-to-point accessories, a lot of times when we're dealing with the PCB, we're just dealing with the stack-up, the copper weights and those type of things, as opposed to the cable here, where we have to deal with things like the grounding or the shielding or the heat shrink. And then lastly, and more importantly, is who are we designing this for? And the question is it for the fabrication we're designing it for fabrication and assembly machines in the printed circuit board, as opposed to the cable, where we're really designing it a lot of times for manual labor. Yes, we can build a cable for machinery, but a lot of times it's got to be done by hand, or especially in low volume stuff. So we're designing it for technicians and manual labor versus fabrication and assembly machines here. So just got to change our mindset a little bit, that when we're dealing with cabling, it's different in many regards than from what we're dealing with on a PCB point of view. Now, a lot of times, cables are an afterthought, and we really can't have it be an afterthought because there's a lot of things that we have to take into consideration. For example, electrical considerations. What signal type are we working with? And one of the biggest issues we got to be really careful about, which we don't think about much very often, but is becoming more prevalent with high-speed design, is this thing called dispersion. And dispersion is basically the smearing of the harmonics of the signal line, signal in time. And the best way to kind of demonstrate this is like a light going through a prism. And with the light going through the prism, we basically smear out that light into its spectrum. Well, the same kind of concept actually happens in a cable as well. So we have to be very careful in particular about cable length. And a lot of this has to do with the fact that, hey, look, with insulators, they put the insulator on, but they're not so exact, so that some of the insulator might be thicker in one area and thinner in another area. And because those dielectric constants are changing, it changes the impedances, which in turn actually causes this phenomenon known as dispersion. So that's one of the biggest things we have to worry about. And of course, it's really more for high-speed design. There's also grounding and shielding, and we shouldn't confuse these two, because grounding and shielding are actually two different things. Grounding is making sure that point A and point B both have the same reference. I actually kind of got a little stung on this a couple years ago. I was working on a particular device that was going from this computer in the lab to a bunch of cameras, and it was working just great, but then when we put it into the final product, it was a very different computer. We weren't getting any signal, and come to find out that the board that they had put into this computer had no ground to it. So after we basically soldered onto a ground to the motherboard and made sure that the connection on the other side was also set up to the same ground plane, everything worked out just fine. And then shielding is a bit different from grounding, though we tend to treat them almost the same. Shielding is basically making sure that we're not emanating out to the world things that are causing issues on other devices, and vice versa, that the world isn't somehow impacting our signal on those lines as well. So those are the kind of things that we have to consider about that. There's also mechanical considerations as well. And there's, for example, the bend radius, okay? And with the bend radius, for example, what can happen if we look at this picture over here is this area under tension can actually stretch. And so a lot of times, for example, there's certain materials that we might purchase that once we bend it, if we bring it back into its linear position, into basically a straight line, it won't be perfectly a straight line because we actually, the material actually stretched on that area under tension over here. So those are the things we have to keep in mind as well. The number of times it needs to be bent, and the tapers and the strain reliefs. Here's an example of one. This drives me a little bit personally batty. That's why I put it out over here. This probably looks familiar to you, but here's an example of a wire that's very, very flexible that is put onto a connector. You probably know what it's for if you ever owned an iPhone. And but what you'll see here is that there's no taper or strain relief to it, and I can tell you that that's probably the most problematic aspect of this cable. I've actually destroyed 3 of them because of the lack of the stress relief on this one particular area. So these are the type of mechanical considerations that we really need to give to our cables, especially if it's going to be a commercial product. Material considerations too, and we'll see this list here in a little bit later on. Is it fire resistant? Is it something that if it does catch on fire, it's not going to put out a poisonous gas, especially if it's in a public area like or mass transit? If it's an environment that it has to survive because of severe temperatures, whether very, very cold or very, very hot, also pressures, moisture, chemical exposure, those kind of things as well. All right, let's jump into cabling at this point in time. There are 2 key factors when we deal with cabling. There's electrical connectivity and there's thermal connectivity. Those are the 2 main, then certainly other ones as well. But let's talk about electrical connectivity first and foremost. It is the ratio, and notice the word ratio, I underlined it on purpose, of current density to the electric field strength. Really a nice way of saying how well does the electricity flow. Well, when we're dealing with a ratio, if you're familiar with them, the biggest problem with the ratio is that it is unitless, because usually what's on the top and what's on the bottom are the same type of unit, so they cancel out. So when you're dealing with a ratio, it's relative. And then the question you got to ask yourself is, what is it relative to? Well, this particular standard that's been put out there, and I honestly don't know who initiated this standard, but it's called the International Annealed Copper Standard, basically said we're going to make copper the baseline. And that's why you see up here in any one of these charts that you can find from the cable companies, and they pretty much all pull it from the same source. But copper has 100% connectivity. That's the baseline. And the question is, what is the connectivity of these other materials in relationship to copper? And what you're seeing over here is that the silver, for example, is slightly better, but for the cost that you'd pay for silver is probably not worth just for that extra 5% connectivity over copper. One of the things that I found very fascinating about this is that there's a misnomer or misconception out there that gold is actually a better conductor than copper, and that's not the case. In fact, copper is far more superior in conductivity than gold is, and there's been great debates about that on the various websites. You can take a look at it, but there's no reason to believe that this is lying or somehow been falsified. You can also see that these other materials are out there as well. One thing I do find fascinating is that when we look at something like ENIG, where you basically put a layer of nickel, which has actually far inferior connectivity as opposed to copper, and then we put gold on top of it, which is slightly better over here. The question is, why do they do that? Well, gold has some properties that are very, very useful, like it's very malleable, and it also isn't corrosive, right? It handles the air just fine, whereas copper and silver actually get tarnished over time because it reacts with the particulates in the air. So what they do is you put gold over copper, but the problem is that the gold and the copper atoms will kind of combine to each other, and it actually makes for a worse connectivity. So they actually put a very thin, that's why they say electroplated, because electroplated actually means you're putting layers of atoms. That's how thin that is. You put a very, very thin plating of nickel between the copper and the gold to prevent that migration from occurring there. So that's how they work that out. So they're using the different properties of all 3 of these materials, their strengths, to allow a gold contact, like on a board that you're going to put into a slot. Okay, Here's another way of looking at it very quickly, that if, for example, if we had, let's say, 100 ohm resistance, and we're going to basically spray that on or put that onto a board here, this is the amount of material that you would need in order to obtain that, that 100 ohms resistance. So you can see silver is the best. You'd need a little bit more material for copper. Gold would need a little more material, and so on and so forth. So I just thought this was a really great graphical way of seeing this. Another way to look at connectivity, because we were talking, and jump back to my slide here for a moment, we were talking about percentage of connectivity. But when you look up connectivity, what you're going to find on the internet or in any of your math books is that actually it's the inverse. The inverse of connectivity is resistivity. So we tend to understand resistivity a little better being on the electrical side of things. And obviously also we've taken the materials at 20 degrees C. These things could change over temperatures depending on whether it's hot or cold. So if you really need to get the specifics about where things are going to work or what temperatures you want to work them at, you'd really have to look at graphs and charts, because nothing's going to be linear. Everything's going to be, there's going to be different curves to that based on the temperatures that you're looking at for these materials. Okay. In terms of thermal conductivity, the exact same concept is used. You have 100% as copper as the baseline. Silver's, again, slightly better. Gold, obviously, is kind of less than copper. What's interesting about these numbers here is that the thermal conductivity numbers and their corresponding electrical conductivity numbers are relatively close in nature. For silver, for example, it was 105 for relative electrical conductivity, as silver is 108 for its thermal conductivity. The same thing with the gold, where it was 70 for its electrical conductivity, and so on and so forth. The only reason why you see a few other materials on this particular page over here is that the other charts that you saw came from, I believe, Cable USA. Yeah, pardon me, Blue Sea USA, bluesea.com, and this one over here actually came from Annixter. So that's why the chart is slightly different here. But in the end, their numbers should all match up because they're going to the same standard. The summary that I really want to start with or make here is that you really want to start with copper. All right. Now, what about other materials? Why do they use, for example, aluminum in major power lines and things like that? Because sometimes you need a material that is better than copper in other factors. For example, copper is pretty heavy as opposed to aluminum. So if you're running lines down, power lines, for example, and they're going hundreds of feet between each of the poles, then you may want to use aluminum because its strength-to-weight ratio is far more superior than copper, for example. Or for remating contacts, gold is really useful for two reasons. Number one, it's very malleable, and so it's soft enough so that if you push some type of pressure into it, the other contact will make place, because the gold can be distorted a little bit or scraped or however, so they can make contact. In fact, if you ever worked with it, one of the first jobs out of college that I was doing was with these gold contacts on this Schlumberger ITS 9000 tester. It had well over 400 pins on it, and they were all gold pins. And what happened was that you put this load board, which is just a huge printed circuit board, and it would get sucked down by a vacuum, and it would make contacts to all the pins, all the places on the bottom of this board, and it was all done through gold pogo pins. They were literally pogo pins that you could press up and down, and they were all made of gold. But they did that because it was malleable and it was non-corrosive as well. And then if you're really looking for something that's going to last for a very, very long period of time, and I know people don't really like to mess with this stuff, but what's cool about mercury is that mercury really doesn't fade away in terms of its chemical properties. So you can use mercury time and time again, and it works out great. That's why they used it in relays, because it's basically self-renewing. It doesn't disintegrate or somehow deteriorate over time. All right. Let's talk about stranded versus solid, because this is where flexibility really comes in. Obviously, if you're going to do stuff that's in an environment where there's going to be a lot of corrosion, and assuming you don't have to have the wire moving around a lot, you really want to work with the solid stuff. And you can see it's best suited for outdoor application. But if you need anything with a level of flexibility in it, then you really need to go with something that is stranded. And we're going to see that there's a number of different aspects of things that are stranded here. So let's take a look at those. The general rule of thumb, the more strands, the more flexible it's going to be, and the smaller the bend radius you're going to get. All right, and so the general formula here is that if it's more flexible and smaller bend radius, then you're going to have more flex life with it. The only disadvantage that you're going to get with this is that the more strands you have, the harder or more difficult it is to work with. And if you've ever played with these in the lab, you know that after a while, if you bump them and bruise them a little bit and get them out of get them out of sorts, it's almost easier just to cut them and strip the wire again than to try to somehow get it back into the shape that that's manageable. Now, the number of strands, it can change from 7 or 19 all the way to a couple of hundred. Obviously, if you're going to do that many strands, then the wires are going to be smaller and smaller. And we'll talk about gauge here in a couple of minutes. For 7 or 19 strands, if you're not going to do that much motion with it, things like fire doors that are always going to remain open or remain closed, and yeah, there has to be some flexibility to them, but they don't necessarily have to be open on a daily basis. If you're going to do something like a car door, which could be open 30 to 40,000 times in its lifetime, and you've got a harness that's handling your power windows, your power mirror, your locks as well, then you'd probably want strands between 37 and 49. And the only reason why these numbers are coming up like this is just based on the way that just the strand counts and the way that they twist these. And you'll see different strand versions here in just a few minutes. And then if you got machinery like pick-and-place machines or things that are just going back and forth thousands of times, maybe per hour, let alone days, then you'd want strand counts over 100 here, and those would be the most flexible. When I had asked the fellow at Annixter, the tech guy, about, it's like, how flexible can a wire be? It's like, well, if you want something that's like a wet noodle that's on your finger, then you can purchase that. It's going to have well over 100 strands in it. It's just that it's very hard to work with. So that's the trade-off. But if you can get past the work issues and make sure that the strands aren't breaking off because they're very small, then you'll do fine with it. All right. There are a number of different types of strandings out there. First and foremost, there is the bunch strand. And the bunch strand over here is just basically taking a bunch of wires and you put an insulator on it, end of story. They don't try to configure it in any way, shape, or form. It's the least expensive way for a cable company to make stranded wire. Then there's concentric, and this is why you start seeing these numbers like 7 or 19 or 37, because it depends on the wire gauge that they're using. And again, we'll talk about wire gauge in a little bit later on. And then the number of wires that you have on the inner and the outer layers here. So you usually start with one wire in the center, and then you've got a ring around the inner, we'll call it the inner circle, and then you have, in this case with the concentric, you have an opposite ring, or at least that they're traveling in an opposite direction here on the outer ring. Why would you go with this over here? Really, it's better mechanical strength, and there's also what's called crush resistance. So if this happened to be run over by a car, this will survive better than the bunch, where the bunch may have been around originally, and then after the car or vehicle drives over it, that cable will probably more be elliptical than circular. So there's also the unilay method, so it's slightly lighter in weight. It's the exact same concept as the concentric, which we saw earlier on. However, all of these are going in the same direction, where the concentric actually had them going opposite directions. And then if you're doing something that requires a tremendous amount of strength, then you have the concept of the rope lay. So you basically, the easiest way of calling this is strands of strands. Okay. In addition to that, you may see two other, let's call them adjectives, that are used to describe these different types of strandings. There's compressed and there's compact. Obviously, the most compressed and compact is solid wiring. However, again, if you want flexibility, then we've got to look at this compressed and compact nature that they could add to these cables. Concentric is just basically, as we saw earlier on, and what there is that the wires are not deformed or any way crushed together. They're just basically placed as is, and there's going to be air gap between those wires. Compressed means that they ran it through a thing called a die, and with the die, it basically made it smaller, but you also see some deformity in those wires. And there's nothing wrong with that. It just makes it a little bit smaller. So that's the compressed one. The compact one, what they'll do is they'll actually run the individual wires through a die, and they'll make it trapezoidal. And so they'll put them in here very strategically in such a way that if you look at the cross section here, it almost looks like a mosaic. There's just no air, or very little air gap here whatsoever. So again, there's costs associated with these things, but if you need that type of type of strength with the smallest diameter possible, these are things that you can consider. All right, I keep mentioning gauge. Let's talk about gauge, because there is this thing called AWG out there, and it's an interesting creature to say the least. So the AWG was created by a company called Brown and Sharp in 1856, and that company was actually still around as long as even in 2001. It was finally bought out, oddly enough, by a European company called Hexagon Metrology. The reason why I find that a little bit odd is because here's a company that actually created something based on imperial units rather than metric units. But nevertheless, they're the ones who created it. Sometimes you may see, instead of American wire gauge, you may see B and S, which will stand for Brown and Sharp. It's one and the same thing. It is not used in steel-based wire. There's actually several other gauges out there. So this is not used for anything for, like, I'd say civil engineering type of things. Its original purpose is for clocks and watches and mathematical instruments. We got to keep in mind that in 1856 over here, though electrical concepts were certainly being discovered and they were being experimented on, it had not really been brought to a commercial use. And just to give you kind of a timeline of history, Nikola Tesla and Thomas Edison, who are basically the two biggest players in the commercialization of basically electrical energy. Well, for Tesla, he was either born in 1856, I think he was actually born in 1857, but nevertheless, obviously he was not able to contribute much in 1856. And for Thomas Edison, he was only 9 years old. So the fact of the matter is that it's really interesting to see that our industry has adopted something that was not made for us initially. Okay, they picked it. We basically inherited the gauging system off of mechanical concepts. So, and back then they were very good with those mechanical concepts. The watchmaking and clocks and those type of things is really considered to be a very prestigious engineering form at that particular time. One of the reasons why they came up with this is this concept of die-drawn. And die-drawn may still be used by cable companies, but it's not the only one that's being used out there. But what they do is you take a wire and you run it through a die, and basically the direction of the motion and the work, you basically reduce this initial wire down to a smaller size. Okay? And there's no waste to it. In fact, it just makes it longer, right? Because the material is just the diameter is being reduced. And so what Brown and Sharp was looking to do was to come up with a die ratio, so from the beginning product to the end product, that would remain constant throughout, that would be optimal for the dies. And so that's what they came up with here. So what they did is they started with two different numbers. They started with 460 mils and they started with 5 mils. And they said, we want 40 steps between this number here and this number here. And we want them to be of an equal ratio. Okay. So when you look at this here, this obviously is the full table. It's really difficult to see. Even I have a difficult time to see, and I've got on a large screen monitor here. But the point I'm trying to make over here is if you look at this, there's some oddities. The first oddity you're going to see is that these numbers don't work in 5s or 10s or 25s or 50s. It's just really weird numbers over here. Well, this is a product of this ratio that I'm going to show you about here in a few moments. Secondly, you'll also notice that the numbers, as they progress higher, that the diameter gets smaller. Okay? And that's one of the things that makes it a little difficult to talk about AWG. You have to keep in your mind that the smaller the gauge, the larger the diameter of wire. Okay? So let's talk about these odd numbers that we're seeing over here. What was the method to their madness? Well, let's take a moment to talk about this concept of geometric progression. And geometric progression, you've probably seen it at one point or another. You just may have not used it recently. But the idea of geometric progression is you start with a number, a given number, and then you multiply, in order to get the next number, you multiply it by what they call a common ratio. So in my example over here, if 3 is my common ratio, 2 times 3 would be 6, times 3 would be 18, times 3 would be 54, and so on and so forth. Here's an example up here in the top right that shows a geometric progression. Actually, it's a visual one, which I like a lot. It's basically a geometric progression of the common ratio being 1/2. Okay. So that's the concept of geometric progression. Well, if you look at the mathematics behind geometric progression, you can get a very nice formula out of this. Now, when I originally saw this, and I'm going to just kind of jump down to this fourth bullet over here. When I saw this initially, you had the 39th root of 92, and I'm like, how did they ever come up with that? Well, it happens to be the result of the geometric progression. The 39 is the number of steps that we need to go from 0.5 to 0.46. So we count 0.005 is really a step already, right? So that's why there's a little bit of a math oddity. So we're not saying 40 steps, we're saying 39 steps. And then secondly, if we look at the ratio that we have over here, it's 0.46 over basically 460 mils over 5 mils and gives us 92. And that's how this equation comes to being. And so that's what they did. They said, look, based on the way we're going to set up the gauges here, this is the ratio we want between each one of the gauges. So for example, if I take the gauge 19 to 18, so we're actually going larger here, then you see that the ratio is the exact same here. And this is true for any two. If I take from basically 9 to 8, it would be the same. If I took it from 36 to 35, it would be the same as well. So that's what the geometric progression allows us to do. Now you're probably saying to yourself, that's fine and dandy, but how do I work with these really weird numbers? Well, the cool part about this is there's two results that make it very useful. First and foremost, if you ever want to double the diameter, it doesn't matter where you start. So if you have a diameter of, let's say, 17, and you want to double the diameter of it, the gauge is 17, then you just basically subtract 6 off or decrease it by 6, and that'll give you 11, and you now have the diameter doubled. Okay? And then one of the areas that we're most concerned about is area, because of the fact that area has to do with resistance, right, or impedance here. If you just decrease it by 3, you double the area. So here's an example of where you decrease it from 13 gauge to 10 gauge, and you will actually double the area on that as well. So obviously these are not drawn to the real scale of the AWG, but this gives you, they're in relationship to each other, they are in scale. So if I took 2 of these and I put them side by side, you'd see that 2 of these would fit in here. Okay? And then of course the area over here, you can see that the area is slightly larger. It's a little bit more difficult to visualize the differences in areas as it is diameters, but trust me, these are actually in scale with each other, not to the gauge, but at least in this example to each other. All right. One of the things that may come to mind is, all right, great with the gauge stuff, but when would I use certain things? And so here's kind of a loose set of ranges. It's not by any means set in stone, and you can still use a 14 gauge wire for signal. That you don't have to follow this, but this is just the general rule of thumb. Basically from 36 gauge to 18 gauge, you'd use it for signal. And again, really the biggest reason for that is it's small, and if you've got a lot of signals, you obviously want to keep the cable or harness at that point to something that's feasible and realistic, and it's not just so big and bulky that you can't work with it. From 18 gauge to 12 gauge, you start getting to what you'd call control. So these are things that would be attached from the printed circuit board out to a panel, or if you're doing mechanical switches from point A to point B, you'd want to have a little bit of a bigger wire, a little beefier wire on that. And obviously, if you've got if you're working with power, 12 gauge on up, meaning the lower the gauge, that you're dealing with power at that point. And one of the things I liked, I found this on the internet, but this to me is a reference of a reference. The site that was showing this over here obviously got it from another site. I don't know where they got this one from, but I like it because it shows you the amount of amperage that each one of these gauges can take. One thing to note here, however, is that, well, there's 2 things to note. Number one, when we're dealing with insulation that's not a part of the AWG. The AWG is specifically in regards to the copper itself. Secondly, the insulation, you definitely want to understand what insulation you're working with, because yes, this wire might be able to take 20 amps, but the insulation may not be able to handle the heat of 20 amps. So you want to make sure that you understand the ratings for the insulation just as much as you understand the gauge of the wire. And speaking of that, and I'm just going to kind of throw this out here because you could probably do a 2-hour presentation on all the materials they've got out there. The list is long, and then all of the things that it's built for are long too. That Annexter PDF, I think, has 2 or 3 pages filled with all the different types of solvents and acids and environments that you might find your cables in here, and these different types of materials that you can use and where they're good and they're not good and so on and so forth. This is a partial list that comes from a company called USA Wire. It's very partial, trust me about that. But it gives you an idea of all the different things you got to take into consideration. Okay, so if you're going to be building for a certain type of vehicle or a certain type of environment, these are the things that you want to think about. Okay, and again, this is where I was mentioning very early on, where we don't really have to worry about these things in a printed circuit board because we're just worried about the copper height, which we do in ounces, and the copper width, where here in the cabling we've got not only to worry about the width of the cable and the type of strand that we're using, but we also have to worry about the insulation as well. Let me jump on to connectors over here. So for connectors, originally what I was going to do is I thought maybe I could show you some examples of those type of connectors and how to connect these things together, how you would basically put the pins into the tooling and stuff like that. And then I realized that there's so many connectors out there, probably what I would show you wouldn't be applicable to 99% of you. So what I kind of did was took it from a different approach just to show you that, look, there's just so many connectors out there. You got to work on the connectors that are based either in your industry or what you worked on before. You got to be savvy about them. They say that, and I say the industry says that there's over 100,000 components in the market. I would tend to believe that at least 65 to 70% of those are connector components, as opposed to chips or anything else that is handling logic, whether it's digital or analog. Okay, so let's take it from a completely different approach. What we need to do is ask core questions. The first core question you want to ask yourself is, can I use a common connector type? Because if you can use a common connector type, then you have a lot of advantages. First and foremost, there are components built for that. So if you're using Ethernet, for example, you have the Renaissance chips, and these chips are specifically made so that when your inbound signals coming in off of your cable through your socket, actually it's not a socket, it's a jack, I'll talk about that here in a few moments, then it goes into these chips over here that can handle the processing of that and in turn provide that to your your microcontroller or microprocessor. And even the firmware support for the microcontrollers and microprocessors are there for Ethernet as well. Though there's one recommendation I'd make, I think this makes a lot of sense, is that I would never run any cable, if you're running a cable into a connector, I would never run that connector that's on my printed circuit board directly into my microcontroller or my microprocessor. I would always put a buffer in there, just because if there was ever a surge on that line, that would protect my processor. So that's just something to keep in mind. Now they may make processors with very beefy internal buffers on that, but again, I'd still like to have some protection on it. That's just an old trick I used to do when we did these boards or made these type of boards. Pre-made cables are available for you as well, and there's always a standard to follow. So again, these are the type of things that you would have if you can use an Ethernet. Now, what if you're building a completely customized harness of this nature here? Then the big question you need to ask yourself is, what have we done before? What are the advantages? You got things like tribal memory. Tribal memory is that corporate, we also call it corporate memory, but it's the memory that we all bring to the table when we work for a company. Our past experiences at other companies, other projects that we've worked on, we bring those to the table, and that corporate memory is really vital. Secondly, do you have the equipment for what we're going to do for this type of thing? Because every time you pick up if you pick up a new connector, one of the first things you want to ask yourself, and you'll see why here in a few minutes, do we already have this equipment? What equipment is going to take for us to make a solid connection between the wire and the connector? And then obviously there's design reuse, which obviously is the golden grail of all electrical engineering, right? Or as much design reuse as possible. And we never always get there, but it's nice to reuse what we can. Now, of course, there are caveats to this. So if you're going to do this, obviously you want to check pin counts. You also want to check the speeds for the wire. Maybe you've been using the same wire for 2 decades, but all of a sudden now you've got signals ripping through this thing that wire is just no longer capable of handling, right? The dispersion of aspects of it. Current handling capabilities, and then there's also voltage requirements as well. Two of the big ones that I think are almost silly, but they're really important, is the history of why it was used. And I always like that story that's told to us about the little girl asking her mom, who is making a ham, why she cut the 2 ends off the ham. And the mother just kind of throws out a reason saying, well, I don't know, I think it just makes it taste better. And the little girl later on goes to dinner at her grandmother's house, and she asks the same question. And the grandmother says, I cut the ends of the ham to make it fit in the pan, right? And so it's really important for us to understand the history of why things were used, because if we don't understand the history, we go down with false impressions of things, or we're doing things that are not really efficient. So that's the only reason I think it's important that we understand why they picked the cable that they picked, or why did they pick the connector that they picked. The last one is qualification requirements. This defense company I used to work at many years ago, we used a part that came from a company called Amphenol. Amphenol makes phenomenal military-grade parts, but there's one particular part we'd used on like the last 3 projects, and I threw my hands up and I said, why do we keep using this part? It doesn't have the pin counts we need. I feel like we keep on trying to park a Cadillac into a coat closet here. What's going on? Why do we have to use this part? Well, they came back and they said, look, this part's qualified. We know it works. And if we're going to try to qualify this other connector that you're asking us to use here, it's going to cost us tens of thousands of dollars in order to qualify it, and we don't have the money on the project to do it nor the time. So that's another aspect that you want to ask as well, the qualification requirements. Now, the big one that you got to ask is what's your environment that this is going to work in. Obviously, the cable has this. You can see the connectors have the same issue as well. Here's just a huge list of it, because most of us, I got to believe, aren't necessarily building appliances for the home. Maybe some of you may be out there doing that, but I think most of the people that are probably attending this today are dealing with environments that are pretty ugly, or ones that can really stress the electronics out there. So if you're working in those environments where it's for the home use, that's great, because then the options are plentiful and it's very cost effective. But if you're working in these environments here, you got to be very selective about the type of connectors and cabling that you're going to use. Here's just kind of a thing I wanted to throw out there. It's a nomenclature of sorts that I think we kind of throw around incorrectly. A lot of times we think of plugs and sockets based on gender, and that's not true. Really, if you look at this example over here, here's an excellent example of all of these up here that you see where my cursor is at the top right corner are examples of plugs. And some of them do have pins, and some of them do have holes. So it has nothing to do with gender. So really the way it's defined is that plugs are always the cable and the connector. Okay? And the socket, and this is what I found very interesting, there's a difference between the two. Most of the time what we're actually dealing with is a jack. We're not really dealing with the socket, because a socket is defined as plugging one device into another. So here's an example over here. This came from a website called Computer Hope, which I really like, because they're the ones who explain this in a pretty decent fashion. They show over here an example if you wanted to switch out, for example, your CPU. Well, you have a socket that's used to swap out that, because you're inserting one device into another, as opposed to a jack, which is what I think most of us are using 90% of the time, where you're basically plugging the cable into a mounted receptacle. That's really the way to look at it. And obviously there's also this term called port. They were trying in a kind of a soft way to say the ports had holes in them. I'm not sure I completely agree with that. Maybe for computers, but I'm not sure if that's true for all devices out there. But again, I'm not a keen fan of declaring something to be a port or a socket or a plug based off of gender. It just doesn't work anymore with the number of connectors that are out there. All right, if you're going to buy it, you got to buy all the pieces. And here's a great example. This thing we've seen around forever. It's your typical serial port. It's your sub D9. And your sub D9, if you ever just want to buy this piece alone, it was $2.50, and you can solder it straight in there, and it will just dangle off your wires. But what if you want other things like back shells? What if you want to have certain pins, like you maybe want gold-plated pins, as opposed to the regular pins that they provide for it? Maybe you've got to have a very rugged back shell. Maybe you've got to have a certain type of grommet that's going to protect the wires. Then you have to start buying different pieces for that. And that's why it's really important that you spend the time to understand all the options. If you ever look at the data sheets, it's phenomenal the number of options you've got. And probably my biggest complaint about most of the websites and the data sheets is they don't show an example of every single one of them, but they just have a phenomenal number of options that you can purchase. And here's a great little example of one. Here's a kit that you can buy. It's a real kit, and this is the real price as of 2 or 3 days ago when I was putting this together. You got the housing with it. Here's your back shell. Here are the screws to lock it down, and here are the jack screws so you can basically tighten this into the device so that you're not putting all the stress onto the housing. The individual pins that will be placed into here and then crimped onto your wires, and an assortment of grommets. So it's pretty complete. Now, can you buy other things for it, like stiffeners, or can you buy a different back shell for this? You probably can. As a matter of fact, some people just buy this kit, throw out the back shell that comes with it, and use a different back shell. So you've got that option here. But again, and this is the zinger right here, is that don't forget the crimping tool. And this is why, again, you want to talk to your technicians, because if they don't have that crimping tool and you're building this for something that's got any level of reliability to it, you don't want to use a pair of pliers. You actually want to use the appropriate crimping tool, and this is $700. Okay, so if you say, I'm just going to use this one for this one particular project and I'll never use it again, well, think twice about it, because there's a tooling cost that's involved in that. So that's why I want to bring that to your attention here. All right, let's talk about drawing some stuff here. There are 3 considerations that we want to give to a cable drawing, and I recommend that we do all 3 of them, because each one has their advantages and disadvantages. So when you're doing a cable drawing, I always recommend that physical representation, because one of the things that these technicians will do, they've seen them do it many times. In fact, I do the same thing too, is that when I get a bunch of these pieces together, I'll actually print out the drawing, and I'll place the pieces where I know they're supposed to be so that I've got my orientations lined up and so on and so forth. It's kind of like doing a puzzle, right? If you're doing a puzzle, well, what's a huge advantage to doing a puzzle, or one of the advantages you can get when you're doing a puzzle is when you've got the box to show you the end product. If you just get a puzzle and you have no idea what the end product looks like, it becomes very difficult. So that physical representation is very, very useful for the technicians or for anybody who's putting this together. Now, one thing you'll notice is that generally speaking, you just represent the connectivity with a wire or a line here. And the reason you do that is because if you try to show these individual lines like this coming out of here, it becomes extremely difficult, and it really doesn't buy much for you. Now, this is 8 pins. If you imagine something that's like 24 pins or 50 pins coming out of it and drawing the wires, it just wouldn't make practical sense to show it in a physical representation. So how do we show it? Well, one of the ways we can show it is through a symbolic representation, and this should look a little more familiar to you because it looks a lot like a PCB schematic drawing here, where you're showing the pins here and you're showing the end result here. You can also show them crisscrossing each other. This was kind of a very simple example that they're providing where everything is one-to-one. Most of us know that's rarely ever the case, but if you can, most of the tools are generally good at, especially the cable tools are good at changing these numbers here so that you don't have to show the crisscross here. Again, very, very good for visual representation, but if you've got a large number of pins, it's a little bit difficult to follow when you're trying to assemble it. So the last way, which is extremely useful, is this thing called the tables. And the tables are really useful because now you don't really have the physical representation, but with a table, a technician will take a ruler and they'll say, oh, I've got J1, P1 to J3, pin 4, and they'll make that connection. When they're done, they move the ruler down to the next line, and it's very easy for them to follow that. And obviously, that's the advantage of this, but without the physical representation, it makes it a little more difficult for them to visualize it. So the recommendation is show all three. There's no reason not to do it, other than the fact that there's probably a lot of work to be done in order to show all of those. Which brings us to our next point. If you are, the best thing that you can always start off with is if you can work with product that's already pre-built and that you can buy off the shelf, what they call COTS items, common off the shelf, that's the best way to probably start off, okay? Because then you can save yourself a lot of the effort of trying to do this, if that's possible, right? Where you may have to do some type of modification to it is if it has to be ruggedized. Maybe it's like, okay, I can buy this, but I got to put some additional coatings on it. That will require a drawing. If you got to add some type of modification to the wiring itself, and I've actually seen them, they do sell them, but if you needed to actually put in a ground, like a ground shielding on this, there's actually an additional loop that you can add to it. So that would also call for a modification or a drawing for in order to show that modification. If you use an unconventional connector, where, for example, you decided to put one end on an Ethernet cable, you decide to put a sub-D 25 pin and then use a configuration that's not following the protocol, then you'd obviously need a drawing for that as well. And then there are company policies where they don't want you to use these things. If this is not Ethernet, then don't use this for something other than Ethernet, or that you uniquely key it so that if there's any field work that needs to be done with it or rework that needs to be done with it, that there's no opportunity to incorrectly connect something from one point to another that would not work. Okay. So how do we draw these things if we got to draw them? Well, there's several different ways we can go about doing this. The first and foremost is the generic drawing tools. And the generic drawing tools are like your Visios, maybe your PowerPoints, shoot, even your Word. Basically, it's something that you may already own or you know it and it's inexpensive, and you just start drawing it out in there. The biggest problem with these, obviously, is there's really no intelligence in the component. So if you have a component, you draw a component out there, there's no properties to it. There's no bill of materials that gets created from it. So everything is either manually drawn, which takes a tremendous amount of time, and there's an amazing amount of opportunity for error in that, or there's scripting that can be written to help automate if you're smart and Visual Basic, or if you look around, I think there are some tools out there that people try to build to help customize these Visio installations in particular. And they may not go all the way, but they can get you there a little bit faster than just manually drawing it. The other thing is using a tool off-label. And this is what we see very often in the EDA industry. And what do we mean by off-label? It's actually a medical term, and it comes from the FDA. And it's a term that they use in situations where a prescription a prescription drug is actually used for a completely different purpose than what the drug was actually created for initially. And in an odd sense, we do that quite often in our industry as well. In the electrical industry, a lot of times we use whatever drawing tool that we've got for purposes way beyond what its intended purpose was. So you can see this goofy example I did over here, where a couple of years ago I was trying to figure out the amount of square footage of grass I have in my yard, living here in San Diego with our drought. I was trying to figure out if it was cost effective for me to go on one of the water saving programs, but I needed to know the square footage, and obviously my house has anything but rectangular blocks to it. So I know Altium extremely well, so I was able to use that. But in the end, unless I wrote a script, which I didn't do, I had to count all of these blocks out to see what square footage I had. And so I was basically using Altium in an off-label manner. Okay, and that's what we see quite often with things like system-level design or even cable design as well. We tend to do that with these tools because we just know the tools. It's like, it's good enough. We just got to get a drawing out there. But we also come to disadvantages as well. The biggest disadvantage that I found with any EDA tool, if you're trying to do cabling, is that we have a problem separating the physical from the symbolic. So remember, the physical representation, let me zip it back over here to refresh your memory. This is the physical representation. It looks like the actual part. Okay? And then you have the symbolic representation, which looks like the points that they connect up to. Okay? So let me go back over here. So the biggest problem that you have is separating the two off, and that's why for the longest time we really couldn't figure out how to get these things drawn in something like Altium or any other EDA tool. So once we figured that, we realized that you had to separate the physical from the symbolic, we were able to do it. However, you see a lot of other limitations that you have. First and foremost, you got to get smart about the components that you're using. Here's an example of a heat shrink. This has a physical representation, but it has no symbolic representation. Okay? And in this situation over here, you may be asking, why did we have two parts over here for a top and the bottom? Because another aspect of schematic drawing in the electrical world is that we can't scale it. We can't redraw it or in such a way. We can't modify the properties or go into the primitives of it. Once we've dropped it down the schematic, it's locked. So this is a crafty way that we came up with to show the top and the bottom of the heat shrink. For something like connectors, we had to show both the physical and symbolic representation. And again, we had to be very crafty about things like, for example, you have we can't separate the symbol from the physical, because if we have the physical, and the symbolic showing as two different parts, then they're going to show up twice in the bill of materials, and we didn't want that. Okay. And then over here, one of the things we had to be careful about is the orientation. We had basically 5 misstarts before we finally got this to work in some form or fashion. So again, these are the things that we are held against because of the nature and the process of the schematic design itself. And for the cable, you don't have a physical representation. It may make sense to draw a line from point A to point B, but really it's the symbolic representation that you have here. Other disadvantage that you have for the bill of materials. When we're dealing with printed circuit boards, we buy X number of resistors, Y number of capacitors. It's all quantity. But when we're dealing with cabling, we could have something like listed in length. So cable wire is listed in length. The heat shrink can be listed in length, or it can be put in as required. So you just buy a spool of it, or you just buy several tubes of it, and then later on you cut it to the size that you need it. Dimensions have to be manually drawn because, again, in the electrical schematic world, we have no dimensions. Schematics are dimensionless, right? So all of a sudden we're turning a dimensionless tool into something that's got dimensions and scale. And then lastly, if you want to do something for like tables, for example, you would have to do a script for it, which we never got around to because we were just busy drawing cables. For supply chain connectivity, for example, that's one of the things that we expect from all of our tools now. For example, with Altium, they have a supply chain panel which goes to DigiKey or to Mouser. Well, we would expect the same thing for cabling and wiring as well, right? And that's the question you got to bring up here. It's like, okay, well, if I'm using an EDA tool to hook into these providers here, can I get to providers other than components that I use for printed circuit boards? And there is crossover from like DigiKey, for example, but what if you wanted to go to Annixter? Or what if you wanted to go to a US Cable or one of these other companies? You wouldn't be able to do that in a PCB tool. So the third type of tool out there is a tool made for the purpose of it, right? The tool is designed for the process, and you can automate most of this. As a matter of fact, this comes from Zukin's First Steps tutorial, and if you're really good at it, you could probably whip this out in between 5 to 10 minutes. and the table itself is completely automated, right? So what the idea is that, hey, let's take those things that would take us a long period of time, and how do we automate those to the best of our abilities so that we can just simply pull from a library, drop these things down, connect from point A to point B, forewarn us if we're using the wrong gauges, and to put together a table for those things that did work, right? And obviously the biggest issue we got is a learning curve. We're always working on the fly. So, but those are the different ways that we can draw this thing out. Now, in terms of this cabling tool, or E3, I'll just throw this at you. If you're drawing more than 6 cables per project, or if you're also finding yourself doing system-level design, I know most of us electrical engineers seem like we're thrown wherever it's needed. So if you're doing system-level design all of a sudden, and you really need to go to something above and beyond a PCB tool to draw those things out, if you're actually doing form boards, or if you're even doing panels for large systems, then you may want to actually give E3 a look-see at that point in time. So with that, I just want to throw this out at you. That wraps up our presentation here on the cabling, and I was able to do this pretty much under an hour. What I wanted to mention to you is that if you wanted to get a demo version, feel free to go on to our website here at 9.connects. You get the evaluation. If you fill this out, we can get you a demonstration of the E3 so you can give it a go. And then feel free to contact either one of our representatives, Jason Johnson or Christopher Che. So with that, we are going to put a poll up. Feel free to answer that. We'd just like to ask you a quick question with that. And the other thing I'll mention to you is that coming up in a couple of weeks, we will be doing our next power dive on inductors. So you'll hear from my good friend Jeff Condon on that as well. So we're going to leave the polls open here for a few more minutes. If you have any other questions, feel free to put those into the panel. Thank you very, very much for your time. Hopefully you learned a couple of things about cabling and connectors, and we look forward to talking with you again in about a month from now. You have a great day.